Here's some headphones I built. I built them over about 6 months with a lot of hard work. They're electrostatic headphones. They're open back, so the sound you hear is the sound coming from the headphones. And here's an amplifier printed circuit board I designed for them. And I'm going to try and share with you what I learned in this video. Here's an example of what can be shipped. This is my black headphones. These are handmade, and that's my logo there. And this is the harness. It's also handmade. You can see the workmanship and the quality of it, and they all get tested and I listen to them. And here's an example of the red one. And this is a very thin film in there, so you obviously don't want to poke holes through it or anything like that, but they've been fairly robust. I hadn't had any issues with them, and they work really well and sound good. And they're open back, of course, so you can hear a little bit of sound leakage, which is not a problem because these are kind of more for just casual listening, and they provide some very good open, airy sound to them. I really like it. This is the bill of materials, which I can provide, and all these parts can be ordered off DigiKey because I do need the special amplifier. There's a schematic that will also be provided, and here is the response, the frequency response of the headphones, and then of course you'll get this, which is the pinout for the connector. So, and I can also provide one of these guys for free because you can usually buy a pack of 5 of them for like $8 or something, and so you probably don't want to buy all of them, and like you probably need one, so I can throw that in there as well. Also, there's opportunity to build vacuum tube amplifiers and different sorts of methods of driving these, and so I think the key is really learning about how they work and understanding what the possibilities are for these this technology. I finished soldering, and I took some alcohol and a toothbrush, and I rubbed the surface, or I scrubbed the surface of this board to make sure I remove any residue and any solder balls. I went through it with a magnifying glass to make sure that there are no cold solder joints and then there's no missing solder and there's no shorts. And I want to make sure that there's enough airflow between the resistors, so I don't tie the resistor directly to the board, so that there's enough airflow here so that this can dissipate the heat it needs to dissipate. These resistors here will dissipate a lot of heat, including these FETs. I made sure that these FETs are oriented in the right direction and the thermal pad is facing this way according to the silkscreen. And if these capacitors or any electrolytic capacitor is not polarized in the right orientation, there will be a lot of problems that are going to be difficult to troubleshoot and may be catastrophic. I make sure that all of the diodes are oriented in the right way, that the line matches up with the line on the silkscreen of the board. Since the transformer secondary windings connect to here, I'm going to do a sanity check and just make sure that they're not shorted out in here. I'm measuring 19 mega ohms because the transformer is expensive and I don't want it to fuse open and lose $70 because I blew up a transformer. I want to make sure that I have 2.8 ohms, roughly 2.8 ohms from the gate of each FET to negative HT, and then I want to, if I don't have 2.8 ohms, I want to adjust the potentiometers here so that I get 2.8 ohms, because before I power this up, I want the outputs to be biased as close to 0 volts as possible so that there is the correct amount of current draw. Remember, the voltage is operating with a positive 380 volts
DC and a negative 380 volts DC, and the outputs of the FET need to be biased at 0, right in the middle. And if the outputs of the FETs are biased at too low, then you're going to be drawing a lot of current through those resistors. So before I power this up, I want to make sure that it's biased correctly. So I'm measuring from each gate to the negative terminal. And this makes more sense when I look at the schematic. Here's the chassis I made. One of the most important things is the vent holes here. So I bought this chassis off eBay, and then I drilled these holes as vent holes for some airflow. And then on the sides as well, I drilled some holes so that there could be some airflow could get in through the sides and then come out the top. So that's one of the most critical parts of this build for me, was to get enough airflow so that all the heat that's dissipated from this board has somewhere to go. Otherwise it'll just collect inside and possibly damage components and be a big issue. Here's a potentiometer, and here's where I connect the headphones, and here's my little logo here. This is the transformer I'm using. Here it's a power transformer. It's the 272BX from Hammond, and I only use the 600 volt center tap as well as the 6.3 volt AC. So the 5 volts I don't use, but one could use that to create maybe a separate rail for a fan or something like that, which originally I had the idea of doing, but right now I'm not doing it. So I created this slot here to put a fan that could blow air this way. And then I have an AC switch here, and I have a fuse internally, and the D block there for the power. I always make sure that I have a ground here. This ground is connected to the chassis for safety. And then this is the input here for the audio, 3.5 millimeter jack. Here's the chassis I'm using. It's about 8 by 6 inches, which is barely big enough. I have the input coming in here, and I have a pin out for the high voltage signal output. I have the audio coming in through this connector here, which is the 3.5 millimeter. It gets routed, goes all the way to the potentiometer for the volume control knob, and then from out of there it goes to this end here, because that's where the audio input's going to be. I have a fuse here for the AC line control, which then goes to this switch, and the fuse is heat shrink to not expose any sort of 120 AC. I have the ground pin then connected to the chassis so that the chassis is grounded, and then the neutral pin will then connect to the transformer here. Okay, so I have everything connected now. The header for the headphones, all the wires now connect. I have right positive, right negative, the bias, and I have left positive, left negative, and the bias. The two center biases are connected together, so only one needs to be connected, since it's only one's routed to the main header, and the center one is the bias. And so the in the harness, this gets split off into two to go to either end for the headphones. So there's a certain pin out for this, which I have, and so that's connected there. And then also the inputs for the audio is here, and then you have the AC here, where you have the 6.3 volt AC connected there, and then the 600 volts center tap is in the middle, and then just the two other poles are connected that way. And then I have other things tied off, like this is the 5.3 volts, and you have the neutral wire there, and then the AC 120 volts AC connected there. I am going to take some measurements.
So I have about 15 volts there and about 8 volts there. Okay. Here I have about 4 volts, 4, 4, about 4. So I think that's good enough. It should be 0, but I'm not going to adjust the potentiometers to get it any closer. I think 4 is close enough, considering this swing is quite high. So if I connect from ground to the positive terminal, 377 plus, minus 376, so no major issues there. Here I'm just playing a 1 kilohertz sine wave, and I'm just measuring basically each output, and you can see that the voltage is about 200 volts amplitude. So I can measure each one, and the positive and the negative will be out of phase from one another. So it works. I have a CD player connected, playing some music, and I played a YouTube file of left and right stereo so that I knew which one was left and which one was right. And I got lucky, I didn't have to flip the polarity of the left and the right, and it worked really well. I connected it with my cell phone first, and there was no awful cell phone noise and things like that, which I had issues with a previous design, which I resolved. So sounds really good. I was really happy with it. I had to leave it kind of sitting there for about a minute or less than that to kind of get to optimal loudness and quality, because it does take a second for I noticed the mylar or the electrostatic film to really charge up to optimal charge and bias. So sounds great. Super happy with the outcome. One thing I tried to do was when I drape the wires back there, that I don't drape them over these resistors, because together the resistors and the FETs are dissipating a few watts. So if they do come in contact with the resistors, especially the black ones or the FETs, the wire may even melt and could cause shorts and other problems. So it's very important that I have good wire management. Here I have a pair of DSP ears, so I'm going to use this guy to take some frequency response measurements of the amplifier and the headphones together and see how it looks. Okay, so I have my headphones hooked up to the measurement device, and you can see here this is the frequency response of the headphones. And what's characteristic about electrostatics is they're very flat, going from 20 here all the way up to about 2 kilohertz. Then you start seeing this pattern, which is quite characteristic, but it's when you get up into the high frequencies, the wavelength is so small that it's very difficult to get a flat response, because now you get into the ear canal and things like that and the reflections. So in comparison, here's an AKG. So that's the AKG K92 that I measured, and it looks like that again compared to my electrostatics. Sennheiser 598Cs, and again compared to my electrostatics, you can see that it's flatter. Don't look at the level of it, the volume, because that's all relative, but the response or the curve is what you're looking at. And here's some Bose QC25s that I measured. That's what they look like. So yeah, compared to the electrostatics, it's quite flat, and you can see even Bose and everyone has troubles in these high frequencies as far as I can't really hear above 15 kilohertz or so. So this doesn't really matter to me. But some of the very high frequency tones, there is a sound pressure level difference, but it's not really that well perceivable. You'll really hear a lot of stuff, in this range. So the fact that this is very flat has a big impact. Of course, frequency response is not the only thing. There's other factors, but this is one thing that I use to measure to make sure that I get that the diaphragm is tensioned properly, and then
there's no loss in the bass region and things like that. So it's really important for me to make sure that that characteristic is there.
Here's a pair of stacks SR009. I found this on Interfidelity's website. They take some frequency response measurements. I think mine look a little bit better. They're flatter from 20 to 2 kilohertz, and then they don't have as much attenuation in the high frequencies. Data is not everything, but maybe a good indication of sound, but I'm sure these sound really good. They do cost $3,000, so I don't have a pair and I've never listened to them, but it's just interesting to compare and look at the data. Alright guys, well here are the 3 headphones I've built so far, and thanks for watching the video. I'm always looking to learn more, so if you want to have any comments, questions, or concerns, feel free to contact me, and thanks again for watching.